All right, welcome to lecture 4.1 on three-dimensional coordinate systems. It's in this chapter 4 in the textbook, that we start to discuss multivariable calculus. So we finished with our discussion of Calc 1 and 2 topics, and this is where we move into some more advanced topics in this course. In order to get ourselves started, to even be able to talk about multivariable calculus, we need to say some things about multivariable coordinate systems. And in this lecture, we'll primarily talk about R3, or real three-dimensional space. But we will also want a way of constructing and studying the graphs of multivariable functions. For us, the functions in this video, because we're in three-dimensional space, will primarily have three variables, x, y, and z. You should keep in mind how this compares to our single variable calculus situation, where a function has one input variable x, and we can write it as y equals f of x. That involves two variables x and y, but it's a one-dimensional system since there's one input and one output. In this video, we will discuss, again, three-dimensional coordinate systems, and our functions will have two input variables, x and y, making them a multivariable function, and one output variable, z. So the goals in this video are, first of all, to study this three-dimensional coordinate system, R3, then to use the distance formula in certain situations to make measurements in 3 dimensions. We'll briefly discuss the equation of a sphere rather than a circle, which is the two-dimensional counterpart to a sphere. And finally, we'll focus on graphing the function, constructing the graph of a function that has two input variables. Now, all of this generalizes to higher dimensional systems where we have more input variables, but as we're stuck in 3 dimensions, that's what we can visualize. This is kind of the only thing we can actually get our hands on and draw explicitly. So let's get started. Just as a bit of review, probably from your pre-calculus course, if you took this in high school, how do we construct things? How do we visualize things in a single variable function? Well, we can describe things using the Cartesian or xy plane. And the way that we set this up, and I'm doing this carefully on this first slide so that we can mimic this in higher dimensions in a moment. The first thing is we assign something called the origin, which is 0, 0. This is just some starting place from which we can walk some number of steps or units away in two different orthogonal or perpendicular directions, the x and the y direction, and get to any point in the xy plane. So we first assign an origin or a starting place. We call that 0, 0. And then we assign two different directions that are 90 degrees or orthogonal or perpendicular from each other. The axes consists of, the two axes, x and y axis, consist of just walking in only one direction from the origin, either horizontally along the x direction or vertically along the y direction. Those are the axes. Coordinates refer to first walking in the x direction and then in the y direction by some number of units, and you can reverse that and go the y direction first, then the x direction. And finally, each point in the xy plane, and this is really what makes the xy plane so useful for us, every point in the plane has a unique identifier or a unique address, and that's really the ordered pair, the x component and the y component. So if I specify two numbers, 2, 3, that uniquely specifies a point in the plane. And you can see in this picture, I can either walk 2 units to the east and 3 units to the north, or I can walk 3 units to the north and then 2 units to the east, and that uniquely determines this point in the plane. And conversely, every point that you pick in the plane has a unique address or a unique locator given by its x and y coordinates. So that's what's going on in 2 dimensions. How can we build this up in higher dimensions? How can we extrapolate from what we know in 2 dimensions? Well, if we have 3 variables that we want to use to assign information to some problem, x, y, and z, let's first pick an origin where we set all of the variables equal to 0. So 0, 0, 0 is also called the origin in any higher dimension, in this case in 3-dimensional space, but this will be true in any dimensions. Let's assign that origin and think of it as a starting place. And we need to construct, now instead of 2, we'll have 3 perpendicular directions. They all make 90-degree angles with each other. And you can see in this picture, well, the x and y axes, or the directions I'm allowed to travel, are in blue for x, pointing kind of back towards us, maybe towards our bottom left. The y direction in gold here is pointing perpendicular to that, and also kind of to our right maybe. And we also have a room for a third dimension that has a 90-degree angle with these two. That's the z direction that's pointing vertically. So you can think of the x and y plane as just being the gold and blue directions here. And that's sort of like maybe a tabletop or a piece of paper sitting in front of you, but you're also able to travel perpendicularly or orthogonally to that xy plane, and that's the third z dimension. The way that we draw this is actually, we're actually making a choice to draw these arrows pointing in this order. If we go x and then y and then z, that order of placing the axes and these arrows in this configuration is determined by something called the right-hand rule. We're not going to talk about this that much, but the way to remember the right-hand rule is to stick maybe the joint of your hand, stick your wrist at the origin. First, put your fingers straight out along the x-axis. So here I'm pointing into the screen. You'd have to turn your hand around to point along that blue axis. If you curl your fingers, they're going to curl in the direction of the second coordinate or the y-axis. And wherever your thumb is pointed, that's the third direction. That's the z direction. So it's called the right-hand rule. There's a few different conventions for this, or reasons that we use this convention of placing the axes in this order. And you can look to physics for some examples of why this is a good convention. But ultimately, mathematically, it would be identical to do something called the left-hand rule, where we put the x and y axes in a different order and have our thumb sticking straight up with our left hand. So that's just where the name comes from. This is how we draw our axes. And let's get started with some actual geometry and drawing graphs in 3 dimensions. By the way, here's a picture with our counterclockwise or right-hand rule shown that if you move from x to y, then your thumb points straight along the z-axis. So let's try to draw in 3 dimensions the location of a point. And remember that in 2 dimensions, we said every point in the plane, in the xy plane, had a unique address given by its x and y coordinate. Well, the same thing will apply in 3 dimensions. Every point can be uniquely specified by an address consisting of an x, a y, and a z component. And you should think of it again as first walk 2 units, if it's 2, 3, 5 in this example, walk 2 units along the x direction, then 3 in the y direction, and then 5 in the z direction. Let's try to draw this together. I bet you can do this without my help, so if you want to try it, pause the video and then check back in with me after that. I just copy pasted this graph here since it was a really nice visual depiction. You can see the right-hand rule is still shown there. So how are we going to draw in 3 dimensions the point 2, 3, 5? Well, I'm going to start at the origin. Here we are at 0, 0, 0. And 2, 3, 5 tells me a recipe for how to find the address of this point. So I'm going to move 2 units in the x direction. Then once I'm there, I'm going to walk 3 units in the y direction. So if I had started at the origin and gone straight in the y direction first, which you can also do, we would have ended up here. So instead, I'm going to take the same walk in the y direction from after taking those 2 units in the x direction. And you can see actually that this makes a rectangle. It looks actually like a parallelogram, but we're looking from an angle. So if you're looking straight down at the XY plane in this picture, this would in fact be a rectangle with 90-degree angles. Finally, we need to walk vertically in the z direction. And if we had started on the gray vertical axis here, we would have gone straight up. And actually, we'd be off the graph if I'm using those same units. Let's actually compress things and let's tick off some smaller units just so I can draw everything in one picture. So if I had gone starting in the z direction, I would have done this. So instead, I'm going to make the same journey from after doing 2 units x, 3 units y, and go 1, 2, 3, 4, 5. So this is our ending point. This is 2, 3, 5. And you can see also this is going to form a rectangle. It's going to form a few rectangles, actually. But here's the one that it forms with just the z direction. And you can start really filling in some lines. Maybe I'll do this in a different color. I'm going to add some gray lines here just to show all of the different rectangles that are formed. So we secretly have a rectangle here, kind of sticking with one of its edges along the z-axis. That's a rectangle. We had the green one that we already drew in the xy plane. If we had gone x and then z, and then we wanted to do y as the third procedure, the third journey, we'd have this rectangle. We also have a rectangle. Let's see. We've got this one. We've got one down here. We've got one along the back, and that just filled in a few more. So there's actually a whole bunch of rectangles you can draw here. But the important part is this green 2, 3, 5 point is what we arrived at. How can we draw a reasonable diagram of -5, 1, -4? Well, it's going to be the same procedure. So let's get a new color. Maybe let's use this blue color. And this time, maybe I'll go in a different order. I'm going to walk along the Z direction first. Let's go down 4 units. Again, I'm going to tick off some extra units here. So we'll go down 4 units in the Z direction. We will go over 1 in the Y direction. So we're going to go here. So first we do this, then we do the Y direction. And actually, I didn't quite make that in the Y direction. I really want it to be perpendicular to this Y axis here. And finally, we're going to travel -5 in the X direction. This one's a little hard to see, but notice the X axis, the positive X axis is the one sticking straight at us. The reason for that, by the way, is if you forget the right hand rule, stick your fingers along the positive X axis and curl them towards the positive Y axis. So going -5 units will go back into the board. I want to be parallel to the X axis we see in dark blue. So here's where I'll end up. -5, 1, -4. Now I took a journey that went Z direction, then Y direction, then X direction. If you carefully trace this out again, but go -5 in the X direction, then up over 1 in the Y direction and down 4 in the Z direction, you should get to the same spot. So here's a visual description or depiction of what's happening in 3-dimensional space. Let's talk a little bit about the distance formula. We won't use this a whole lot, but it's important to know how to make measurements in 3 dimensions. And part of calculus class is making measurements like area, also volume. We've discussed this semester. And distance is again one of our one-dimensional, or actually it is our one-dimensional measurement, whereas area and volume are for higher dimensions. So in 3 dimensions, we can compute areas and volumes, but if we have a one-dimensional figure like a line segment, or the line segment specifically from the origin out to a point XYZ, then the distance is essentially given by the Pythagorean theorem. And here's how it goes. If I first compute the length of the hypotenuse of the triangle made just by the X and Y coordinates, that'll be a triangle lying flush in the XY plane. And by the Pythagorean theorem, with just X and Y as the legs, the length of this dotted hypotenuse here will be square root of X squared plus Y squared. It got a little chopped off in the picture here, and so did the next one, but this says square root of X squared plus Y squared. Next, we can form a triangle, and this was part of the green rectangular prism that I drew a moment ago for us. We can draw a triangle whose hypotenuse is straight out to the point XYZ, whose one of the legs is the Z direction, so the Z coordinates just Z, and then the other leg is that original hypotenuse. So we're starting with the original hypotenuse as one leg, the Z direction is the new second leg, and then the new hypotenuse is all 3 coordinates combined. If you use the Pythagorean theorem carefully, you will get X squared plus Y squared plus Z squared and take the square root to get the length of this hypotenuse. That's the distance formula. And in general, in higher dimensions, the distance formula is computed by summing the squares of the coordinates of your point and taking the square root at the end. This works in 1 dimension as well, because if you square a single coordinate and take its square root, it's actually the same thing as taking an absolute value. So this checks out no matter where we want to compute distances in 1, 2, 3, or higher dimensions. By the way, we don't just need to start at the origin to compute distances. If you have 2 points, x1, y1, z1, and x2, y2, z2 in the xyz space, what we call 3-dimensional space, then we can compute the distance between the 2 points by doing the same thing, constructing a line segment. And you can essentially treat that line segment as if it starts at the origin and ends at the difference between the 3 coordinates, which would be a completely different point in space. But the idea here is the distance formula applies with that same triangular picture as well. The hypotenuse has length given by square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. Now that's a mouthful to say out loud, but the way to think about this is to compute the difference between each component. The x, y, and z components have differences, square those differences, add them up and take the square root, that will compute the distance for you. So now let's get into the main topic of this video, how to graph in 3 dimensions. So just like in 2 dimensions, the graph of a function or the graph of an equation is some visual depiction of all of the points satisfying some algebraic equation. And for us, we'll officially define a graph to be, for an implicit equation in x, y, and z, to be the set of points whose x, y, and z coordinates satisfy that equation. It's as simple as that. So the 2 sides of an equation are equal whenever we plug in the x, y, and z coordinates of any point on that graph. And conversely, anytime we find an x, y, z solution to that equation, it determines a point on the graph. For example, if you take a look at the equation x squared plus y minus 4 squared plus z plus 1 squared equals 9. Now, if we didn't have the z part here and just had the x and y bits, you'd probably recognize this as a circle. And if you thought about it for a moment, you might even recognize that as the circle whose center is 0, 4, and whose radius is 3, since 3 squared is 9. Now, the same exact analysis applies in this case to say that the set of points that satisfy this equation are exactly those who, if we take a square root of both sides, have the left side equals 3, and the left side is exactly the square root of the distance, or rather, it's the distance formula. It's the square root of the components squared. So the left side is telling us the distance from the point x, y, z back to the point 0, negative 4, positive 4, negative 1. 0, 4, negative 1 is this point. And what this equation is telling us is that all of the points satisfying the equation have distance exactly 3 units away from that point, 0, 4, negative 1. You can see that this is a sphere, and in general, a sphere is always going to be a set of points that are a common fixed distance away from a single point called the center. So 0, 4, negative 1 with radius 3, that gives us a sphere of radius 3 with that center, and it's described by this equation. We can also graph it this way. By the way, this sort of teal-looking circle in the figure here is not any, it's not any meridian or equator or anything of the sphere. It's actually the cross section, or rather the boundary of the cross section of this sphere, cut out by slicing it by the xy plane. So the points on this teal circle are the ones satisfying a certain circle equation in the xy plane. You can see they're given by a circle. And if you plug in z equals 0 and push everything that's not an x or a y to the right side, you'll see you actually get another circle equation in the xy plane. So just like we can chop up 3-dimensional volumes into cross sections, we've been doing this previously in this course, we can chop up 3-dimensional figures into their cross sections using different planes this way too. Let's try our hand at sketching freehand the graph of a function. In this case, we're going to start simple. We have 3 variables, x, y, and z, but let's write down an equation only involving one of them. So the equation we're interested in is y equals 3. Before I draw anything, make a prediction what this looks like. If you had seen the previous example before I drew, or before we had that graph of the sphere, would you have guessed that that was a sphere that popped out of the equation? And in this case, for y equals 3, what shape do you expect me to draw in a moment? So if you're ready, hopefully you've thought about this for a moment. Let's just try to get our bearings. If the y coordinate of my point is 3, let's go out 1, 2, 3 units to the right. And no matter what point I choose on this plane, it has to have y coordinate 3. So if I were just drawing in the xy plane, let's redraw those so they look a little, make them perpendicular to the y-axis. So if I were just drawing in the xy plane, let's just first draw that slice. Oh, that wasn't very parallel. We'd have the line y equals 3, which is parallel to the x-axis. And in this case, you can think of as the horizontal line with height 3. Now here, our orientation has changed. So you can turn your head and you'll see it looks like a horizontal line with the x and y directions. But in any case, it's a line that lives in the xy plane that has a constant y direction or constant y component of 3. But also, we have a z direction as well. So if you think about it, if I walk 3 units in the y direction and let my x coordinate be anything I want, that describes this line. But let's also let our z component come into play and let that be anything you want. So once we're on this line, we can then go up or down by any number of units and get the z component. So really what we're going to have is a plane's worth, an entire plane's worth of solutions to y equals 3. So let's just carefully review this. Any solution to the equation y equals 3 has x and z components, whatever you want. That's why they're called free variables. And y component equal to 3. I'm going to redraw this, by the way, to make everything really look perpendicular and parallel. There we go. That's a little better. Here's our plane that slices through the y-axis there. So any point there that satisfies y equals 3 will have to live on this plane. The x and z coordinates can be anything we want. Conversely, anything on this plane has, well, no information about x and z. It can be any values, but it has to have that fixed value y equals 3. So this is a graph of y equals 3. And you might notice something if you're starting to pick up on patterns in 3 dimensions, that when we have 2 free variables, we got a plane that looked kind of like our xy plane. It had 2 different directions to it. Really, the x and the z directions are completely unfettered or unlimited. What if we, and we'll do this in the next example, what if we had an equation involving more of our 3 variables? So with y equals 3, x and z are free, and we ended up with a 2-dimensional looking plane. What's going to happen if we start including more variables in our equations? Let's take a look at the next problem together. Oh, by the way, just for some important versions of planes, some important examples, just like we have coordinate axes in 2 dimensions, here we actually have our 3 coordinate axes, x, y, and z directions, but we also have 3 coordinate planes. And these coordinate planes are given by the 2 free variable equations, so equations only involving one of the variables at a time, given by setting each of the variables equal to 0. So for z equals 0, this literally is the xy plane. You should think of z as the height off of the xy plane. And if we say that the height is 0, then those are just the points lying in the original xy plane. The graph of x equals 0 is really the yz plane. You'll see this as the vertical one where that's shaded in blue because it has blue coordinate or x coordinate equal to 0, and it's perpendicular to that x-axis. And finally, the graph of y equals 0 is the gold vertical plane as well. It has y coordinate equals 0. It's actually parallel to the green y equals 3 equation that we just graphed. And it has any x and z components that we want. So here are the coordinate planes in 3 dimensions. And you'll see that they're really in correspondence with our coordinate axes. Every coordinate axis determines a plane, and it's the unique coordinate plane that's perpendicular to that axis. So, okay, let's start including more variables. Let's take a look at an equation, in this case, an explicit equation solved for z that says z is equal to x squared minus 3 for any x value. You can think of this as z is a dependent variable, and it depends on the input variable x, but y is still hanging around and is a free variable. It can have any value we want. So how can we graph this? Well, let's think about it. If we fixed a y value, even though it can be anything we want, if we fixed maybe y equals 0 and just looked at the shadow of this graph in the xz plane, this would look like a parabola. It would really look like an upward-facing parabola, upward meaning in the positive z direction, that's been shifted down by 3 units. So if I had said y equals x squared minus 3, hopefully you'd recognize that parabola from single variable calculus. Here we just have a different coordinate plane. In the previous, if we set y equals 0 in this slide, this would be the gold plane, and we'd actually explicitly be looking at a parabola in that gold plane. It's been shifted down by 3 units. But if I then slide my y value around, all I'm doing is taking a copy of this parabola in the xz plane and sliding it horizontally in that y direction. So here's a graphical depiction of what's happening. Each of the cross sections of this 3-dimensional figure look like the curve something equals x squared minus 3. It'll look like z equals x squared minus 3, of course, in general. But we will take a copy of that parabola and slide it along the gold y-axis, really smearing it out in the 3rd dimension. And this gives a shape. You can call this a parabolic surface. It's really called a conic surface officially. And it is a two-dimensional surface. So we should think about this for a moment. We had an equation y equals 3 that gave us a two-dimensional surface. Oh, it was a two-dimensional plane in that case. Here we actually have a two-variable equation, z equals x squared minus 3. That gave us also a surface, but it was a surface that was a little more complicated. It wasn't. It was not independent of two of the variables. It was only really dependent on the x coordinate, and z then depends on that as an output. But of course, in the y direction, we can do anything we like. What do you expect to happen if we use all three of our variables in an equation? Maybe, for example, we had z equals x squared minus 3 plus y. That one's a little harder to graph, but you can imagine taking slices or cross sections to try to get your hands on it. And that's what we're going to learn how to do in a moment. But first, I want to talk about other types of planes, since these are important in 3 dimensions to understand. So there are many reasons to compare and contrast planes to lines. The basic reason that is that a plane can be described by a linear equation like y equals 3 or x equals 3, something with only one power of any given variable. In general, we'll be able to write down plane equations that use all three or two of the variables in a moment. We'll do that together in a moment. But our planes are somehow distinct from lines in that they have more information going on than just a slope and an intercept, or a slope and a pair of points, a slope and a single point, a pair of coordinates. So I'm going to kind of chop out some of the discussion in the book and just focus on this picture and how to think about planes without explaining where everything comes from. But the idea is, if we have, well, first of all, if we have a vertical plane, meaning it's parallel to the z-axis, then we'll have to do things a little differently. But if we don't have a vertical plane, then our plane will have two different slopes or two different directions to travel. This is somehow what it means to be a plane. We can pick two directions and travel infinitely in either of those directions and stay within the plane. So any non-vertical plane will have two slopes. The vertical plane has like an infinite slope, if you want to think of it that way. One of the slopes will measure the rise over run, or the change in the x direction. The other slope will measure the change in the y direction. And the key here is that when we compute rise over run, the rise will be literally the change in height, and the change in height is the z variable or z coordinate. And then the run will be along which direction we're looking to get the x slope or the y slope. I think it's a little confusing to say this in words. Let's say more precisely what we mean by the equation of a plane, at least a non-vertical plane, in 3 dimensions. So let's fix a plane, and if it's not vertical, then it has to cross the z-axis somewhere. If it's not parallel to the z-axis, then it has to cross the z-axis in some location. We'll call that location the intercept, or the z-intercept, 0, 0, b. And if it has two slopes, mx and my, in the x direction and the y direction, described by rise over run for the x and y variables, then that plane will always have the following equation: z equals mx times x plus my times y plus b. Now the key here is this is not a point slope form. This is a slope intercept form, or really a generalization of that to 3 dimensions. This equation involves all 3 variables, but you'll notice that if that one of the two slopes, the mx or my, or even all of them, are 0, then it appears to only depend on 1 or 2 of the variables. So if z were equal to b, that would actually be that would be the x. That would be a copy of the xy plane shifted up by b. So let's just dive in and see how to compute this. We can talk about it all day, what it means in general, but I think it'll be easiest to see this in an example, how to compute the equation for a plane. And to remind you of the ingredients that we need, well, before that, let me actually remind you of the actual plane equation that we just saw a moment ago, which was z is equal to mx times the x variable plus my times the y variable plus whatever the intercept is. Okay, good. So now let's start filling things in order to find these values. Let's actually start with the intercept. So one of these 3 points is actually already an intercept, which is nice. We don't have that in general. But remember, our intercept always looks like 0, 0, b. It's the thing with x and y components set to 0, and just the z value, the z intercept depends on the z value. And I see here 0, 0, 8 has, it lies on the z-axis, so that's the intercept of this plane. I have 2 more points to deal with, but I actually need to compare them to that third point potentially, because what I want to find with mx and my is a change or a rise over run when I'm holding the other variable constant. So the way to compute mx, for example, is it's supposed to be a change in z, that's the rise, over change in x. And if I'm changing in the x direction, I need to not change in the y direction so I don't really screw up my rise over run calculation. So change in z and change in x, I need to find the right pair of points to compute this with. And the key here is find points with, sorry, that's a little ugly, with the same y component, or I'll say the same y value. Again, the reason is if I want to compare rise over run for x and z to compute mx, I need to fix or don't change the y component. Well, among these 3 points, do we see any with the same y component? Yeah, this 4, 0, 0 and 0, 0, 8 both have identical y components. So we'll use those to compute our rise over run. First, the change in z. I'll do the second one with 0, 0, 8 minus the first one. Has z component 8. The first one has z component 0, so there's our rise. And then the run, the z component of 0, 0, the x component of 0, 0, 8 is 0. The x component of the first point there is 4. In this case, we'll get 8 over -4, which is -2. So there's our x slope. This is the change in the x direction for every unit of change in the z direction we travel. I'll switch back to that blue color so I can highlight some different points. To compute the y slope, I want, again, the rise to be change in z, but the run to be a change in y. And for this one, I want to find 2 points with the same x value, just like we did for the same y value previously. 2 points with the same x value. Well, that looks like the middle point we haven't used yet, and the last point, which shows up in all of these computations. Maybe there's a reason for that. In this case, let's do, so delta z, that's 8 minus 0. And the change in y now is 0 minus 6. In this case, I'll get 8 over 6, which is -4/3. We have our b, so we have all of the values we need in order to write out this equation for the plane. It's going to be z is equal to -2x minus 4/3 y plus 8. And you can check, well, you can check a few things with this. These 3 points, I'll show you those points again, all satisfy this equation. And that was what we wanted at the start of the day. Write an equation for the plane with these 3 points. And actually, these are the 3 intercepts along all 3 of the axes. So this is even better. And you can check that plugging in 2 of the values equal to 0 will, and solving for the third value will give you each of those 3 intercepts, 4, 6, and 8. And on the other hand, all 3, so that tells you all 3 of the points on there. And on the other hand, there is a unique plane through all 3 of these points, and this is the equation for that plane. So if you find any other point that's collinear with these 3 points, it has to satisfy this equation. We're not going to do any sort of proof of that, but this is how the equation works in general. Good. Okay, this is going to work in general, but in harder problems, you may not have 3 intercepts. You may have to do a little more work to solve for some components there. So here's the main idea, by the way, in this example. If we have 3 points, A, B, and C, that lie, 3 points in general always lie in a plane unless 2 of the points are secretly the same point. But we know that they have unique addresses, so as long as they have different coordinates, they are 3 distinct points. They might lie on the same line together, in which case there will actually be more than one plane passing through that line. But let's suppose that they don't lie on the same line together. They're not collinear, in other words. But they are coplanar, and to find the equation for that plane, we can first see if 2 of the points share an x coordinate. And if they do, then the y coordinate will be changing, and we can use the z and y coordinates to find the y slope. And vice versa, if 2 of the points share a y coordinate, we can use that to compute the x coordinate, as change in z divided by change in x. But if we don't have that situation, we actually might have to set up a system of equations for m, x, m, y, and b, and try to solve for those numerically. If you've taken a linear algebra class in the past, there are faster ways to do this using vectors, but it actually amounts in 3 dimensions to just doing this explicit system of equations and solving for those 3 parameters, mx, my, and b, and then you can write out the equation for your line. You'll have some more practice on this in the classwork, by the way. So to wrap things up, I want to just briefly talk about higher dimensions, what would happen if we had 4 dimensions to play with, and 4 different variables. And this is important, by the way, when we start talking about sets of data. Maybe we have a probability space given by a set of data, and we want to make statistical inferences about it using multivariable calculus. Well, our space may not just have 3 coordinates, the height and weight of everyone, and then the third coordinate could be their GPA. We might have other, sorry, that was a bit of a contrived example, but I really mean, let's make some measurements on Emory students and the whole student population. Maybe their height, their weight, their GPA, for whatever reason we want to compare those. There might be other measurements we could make, and we need 4th, 5th, 6th, and higher dimensions to keep track of that data, the population data in that case. So for 1, 2, and 3, we kind of already know what's going on with our lower dimensional spaces. A k-dimensional space will be defined as the set of points with k coordinates, x1 through xk. We can write down a distance formula using that same, build up using smaller triangles approach. And the distance from a point out to, from the origin out to a point with x1 through xk as its coordinates will be add up the squares of those coordinates and take the square root. There's really no right-hand rule for higher dimensions, but we don't care so much because we can't draw inside of those spaces. But you can imagine sticking down your x, y, z axes, and then if you had room for a 4th perpendicular direction, you could fit in, the 4th axis, the x4 axis in that case. So that's all I want to talk about today. Here are a few summary questions, and I actually have some exercises at the end of the video as well. So the summary questions just ask you to reflect a little bit about all of the notation and different procedures we've learned. So what sort of things are represented by the notation A, B, C? First of all, we know it's the address of a point in R3 or in real 3-dimensional space, but what types of displacements or distances can be represented by A, B, C, the coordinates of that point? Other than just that single point's location, what else is represented by that? Next, what's the right-hand rule, and what does it tell you about your 3-dimensional coordinate system? What does it mean to have a right-hand rule or have a preferred way of drawing the axes? In 3-dimensional space, what is the y-axis? Can you describe it using a picture? And can you describe it using an equation? Can you write down an algebraic equation like we've done for planes and other surfaces before that would describe just the y-axis alone? And likewise, in 3 space, what is the xz plane different from the x or z axis? What are the coordinates of a general point on it? And what is actually an algebraic equation for the xz plane? Next, how do we use a free variable to sketch a graph of a function or an implicit equation in multivariables? And finally, how do we recognize the equation of a sphere? After you've thought about these summary questions, here are some warm-up problems before the classwork that we'll do in person. I'll just show you these. You can pause and read these on your own. These are also in the textbook. All right, thanks for tuning in, and I'll see you next time.